welcome to this video looking at observing distant galaxies. And well, welcome to you. And yeah, so we're going to have a look at observing distant galaxies and try and see what knowledge has come from those observations and what it has helped us to understand about the universe. This video, same as the last video really, is a bit of a homage to Edwin Hubble, who was a very important astronomer whose painstaking work observing what at the time people originally thought were nebulae. These nebulae, big clouds, which we didn't know what they were. Edwin Hubble was instrumental in helping us to realise that these were galaxies. He took photographs of them that required a great deal of patience and a great deal of hard work with the comparatively rudimentary technology available at the time, and with the telescopes that he was using was able to tell that these were actually galaxies. Now, we spoke in the last video about something that Hubble did was by using Leavitt's work, looking at the Cepheid variables inside distant galaxies, inside these nebula. He was able to work out the distance to these galaxies. So not only did he tell that they were galaxies, he identified them. He then, very importantly, gave us an idea of their distances using the Cepheid variable method. He then did something which was extremely helpful and extremely informative, and this was to do with analysing the light from these stars or galaxies. He found out something about their movement and the way in which they and the universe are moving. Now, to explain this is to get the full detail of this, you're going to need to wait until video 4.1, which is from the section on stars. I'm not going to go into the full detail here. I'm going to give you half the story, and it's the half so that we just know the importance. But to cut a long story short, what Hubble did was he stared at these distant galaxies. So they're not nebula, they're galaxies, and he saw that they were galaxies, and what he did was to do some special analysis of the light. And what he noticed was that the light that was coming out of some of these stars was red shifted. Redshift! What that means is that, so on the top here we've got a spectrum of light from our sun, and we've said before in an earlier video that white light, when you pass it through a prism, can be split up, and you can use a spectrometer to analyze it. Don't worry, video 4.1 is going to explain this in more detail. But basically what he saw was this pattern in our sun and this pattern in a distant sun. Notice all these, where these lines are, and I'll explain the significance of those in a later video. Let's go for a better colour than that. All of these lines have been shifted towards the right. Every line on here has been shifted up towards the right, They are shifted towards the red end of the spectrum. Okay, this is redshift. He then looked at other stars and saw, well, look at this one. This one is even more red shifted. All the lines on this one have been very significantly shifted towards the red end of the spectrum. So different stars and in distant galaxies were red shifted by different amounts. What is the significance of this? Well, this red shift can be explained by the movement of that star. Redshift indicates, so if you're an astronomer and you notice some redshift, that means that the object that's emitting that light is moving away from you. And if you're looking at something that's emitting, or that's got blue shift, that means it's moving towards you. Now, like I said, and I do apologise, but I'm not going to go really into this. What at this stage we need to know is that Hubble spotted redshift. He stared out into space and he looked at distant galaxies and he saw redshift. And he didn't just see it once, he saw it everywhere he looked. All of the galaxies around us, he saw this redshift. And that meant that all of the galaxies in our, well, not just in our neighbourhood, all of the galaxies out there seem to be moving away from us. Now, I've already mentioned that he's seen this redshift, but he's also using the Cepheid variables to measure their distances. So he looked at the redshift and he looked at their distances, and from the redshift you're able to work out the speed of something. If it's redshifted a little bit, it's moving away from you slowly. If it's redshifted a lot, it's moving away from you very quickly. So he could work out the speed of galaxies and their distances, and he did this. He trained his eye, or his telescope, on hundreds and hundreds of galaxies and spotted a pattern. He spotted that as the distance, so down here, look, this is 0, as the distance increased, and look, the scale here is in parsecs, the velocity increased. So looking at all the galaxies out there, he found this pattern, that there is a proportionality between how far away a star is and the speed of recession. So I've got this velocity, but this is the recession, and we call it recession because it's moving away. They're all speeding away from you. So this was a pattern that he spotted, and he noticed this proportionality. The further away, the faster it's receding. Now just take a look at his data here. He saw this and was able to come up with a line of best fit, but can you spot we've got actually a line of best fit and there's a dotted line of best fit as well, because at the time his data was limited. This was only for the number of galaxies he'd looked at, and it was only with the techniques that were available to him. So his measurements and his techniques weren't as sophisticated as they could have been. So there was some uncertainty. And you guys will have seen this when you do experiments in school. Depending on the limitations of your equipment and time, you do get a degree of uncertainty. And I'm sure every scientist has drawn a graph and tried to draw a straight line where they think it might not belong and get a wrong answer. So he started out with this problem. Since Hubble came up with this straight line, and since he came up with this idea, there's been loads more contributions, loads more data points, much more accurate points, and we've in the last 10-20 years got a much better idea of where this straight line should be and of this relationship. But importantly, there is a relationship, and this shows that velocity is proportional to distance. So this is the velocity or speed of recession. It's proportional to distance. And if two things are proportional, we've got this constant of proportionality. That's why we've got a straight line graph there. So what Hubble found was, and what he was able to come up with, is that this speed of recession is equal to the distance multiplied by this constant, the Hubble constant. Now let's just have a quick look at the units here. The speed is in kilometers per second, and here we've got Hubble's constant. The units are actually kilometers per second per megaparsec, multiplied by distance, which is in megaparsecs. Now when you multiply these two together, megaparsecs are going to cancel because this is divided by megaparsecs, this is times by megaparsecs, so we end up with the same units on both sides. So it is a strange one, this number, and it's got very peculiar looking units, but this is a relationship that Hubble was able to come by studying huge amounts of data, loads of different galaxies, and checking out their behaviour. This picture here sort of tries to help us to visualize what he was seeing. This is an idea that the galaxies, over time, the distance between them is increasing. So look, I'm going to go for this yellow one in the middle. That looks a bit like our sun. And over time, the distance of these things is increasing. And so Hubble could see this general pattern, but what he could also do was to look at all the data on all these different things, and what it suggests is an expanding universe. Everything is moving away from everything else. All the distances are increasing, everything is spreading out, and it's continuing to spread out. And the way that it's doing it, things that are close to us are moving more slowly than things that are further away. So the things at the outside, these objects at the outside, are the ones moving fastest. So their distance gets bigger and bigger and bigger. And this is an expanding, and it's a pattern that is typical of an explosion, a sort of spreading. And in an explosion, and in this sort of pattern from this, what it suggests is that a long time ago there was a huge blast of energy sending stuff out, and the stuff on the outside is moving fastest and the stuff on the inside is moving slower. This is amazing evidence, overwhelming evidence for a Big Bang.
Was there a Big Bang?
And this is the idea of how the universe might have started, way back with some huge energetic propulsion pushing all the galaxies out into loads of different directions. So before you even start thinking about what was going on here at the beginning of the universe, what we've got is data and evidence from thousands of different galaxies which all support the idea that they used to be closer together than they are now. And they all support the idea that the universe is expanding, and they all support the idea that there was an explosion. So this is extremely heavily evidence-based. This isn't an idea that scientists have plucked out of the air and thought, you know what, it would be funny for us to say this and try and convince religious people that it actually started with the Big Bang. There's a huge amount of evidence and a huge amount of data to support this. There's also a huge amount of science going on to try and explain what on earth is happening here at a point when all these galaxies were stuffed into a tiny, tiny space. And there's experiments continuing to study this. We're still trying to work it out, but this is the best theory, the best idea, and the best knowledge that scientists have. I'd also just quickly like to say there's no reason that religion can't, or when I say religion, what I mean by that is that the idea that this was created, this event, that there was some God who played a part in this. Well, it seems perfectly reasonable to me that the Big Bang happened, but maybe a God made it happen. That could have certainly, yeah, those two ideas can coexist. So I don't think you need to think of this as the Big Bang as a battle, Big Bang versus God. No, like those two ideas can coexist, but there's such overwhelming evidence for the Big Bang, it seems foolhardy to me to reject it and to not put some faith in it. But we're getting a bit philosophical there, aren't we?
Now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
So, observing distant galaxies. Hubble. Hubble's the main man who we're paying dedication to today. And what did he do? He identified that the nebula were galaxies. He worked out how far away they were by studying the Cepheid variables, which were very important and instrumental to this whole thing. And then he also found out about the movement of these galaxies. The universe is expanding. And how did he know this? He saw Redshift. The idea, very briefly, the idea that the light, the pattern of light given out by stars, is shifted to the right. And if it's shifted to the right, it means that it's moving away from us. If it's shifted a bit, it's moving away from us slowly. And if it's shifted a lot, it's moving away from us quickly. And if it's not shifted at all, it would be stationary. So Hubble saw this movement. He worked out that the universe, it supports the idea that the universe is expanding, and that supports the idea that this universe of ours started with a Big Bang.